Okay, are we back? Let's see. So it's 9,000 flat, and then it goes down. But then it should go back up again. Let's see. Is everything okay? Wait. Oh wait, I think I can see I can see myself in this other device. It's sounding okay. If I scroll on the VS Code, it's not gonna lag. It lags a little bit only, but like only the screen part. If I move constantly while I scroll, then it hopefully won't. Oh shoot. Wait. So if I move, okay, what happens if I disable the camera? Okay. And now I just like scroll. Ooh, smooth like butter. And now if we re-enable the camera, it should be fine. Yeah. Okay. Well, if somebody works at Apple or OBS, take a look at the at the camera widget, because if you disable it, it like fixes itself, and then you re-enable it, and then everything goes back to normal. I might be lying actually. Brother, what's going on? Please. I don't have any other programs open. It is possible that like Firefox is maybe acting in the background. Let's take a look at the activity monitor. Or maybe not. You'll discover my Bitcoin mining operations. Illegal Bitcoin mining operations. It's okay. So can I... why is there a Firefox process? Very suspicious. So if I sort by CPU... Yeah, all of these seem fine. Firefox, why are you still awake? Oh, I just need to quit it. Let's see, quit. Suddenly all of our problems disappear. Let's see. Hello, Firefox. Firefox. Okay, then the activity monitor we can also quit. And so now things should be fine. Let's see. Is it fine now? Let me refresh the stream on my end. And it should be fine. Yes, it seems. But don't be deceived, because OBS can just start acting up. Yeah. That's what I'm noticing here on the other device I have. If I don't put the camera, and then if I enable the camera, it starts to lag, right? Maybe. Is it lagging? I don't see it lagging on my end with the camera on. So like before I was. So the immediate moment I click VS Code, things are gonna go south. So 3, 2, 1, let's click VS Code now. Are we still on? Yes, we're still on. Yeah, if I scroll fast, you're gonna see it go fast. Yeah, yeah, no, we're back. Sometimes it lies, sometimes it does not. Okay. I mean, what? Yeah, it's very strange. It just does whatever it wants. Um, I mean, uh, you know, at some point in time, we're going to say we used to pray for times like this. Once all of the issues are solved, these are the times where we're praying. These are the times where we're praying, so that in the future we can say, I used to pray for times like these. Currently, I think it's working. I think it's working now. Because like OBS behaves in such a weird way. The same. I think the problem is not OBS. The problem is Mac. Like, if I and I think I said this before. If I change the resolution to 720p, stream for 3 seconds, stop that, and change back to the original resolution, which is 1080p, it like works flawlessly for absolutely no reason. So I don't know. Maybe I don't know. Maybe it resets something. Maybe it like does something to some memory buffer that they have, and then it like no longer there's a memory leak. I have no idea. Either way, um, life is beautiful. Life is beautiful, and today is one of the days that constitute life, and as such, this day is also beautiful. Yeah, I don't know why I said that. It is true though. It is true. You gotta live every day to the max, I suppose. Okay. I think we're good. I think we're good. It should be stable now. If it ever gets unstable, I'll just disable the camera. It's okay. It's okay. You know. So, anyways. Welcome back, everybody. Welcome back. Welcome to the greatest event, the greatest streaming programming. um, Today Tuesday is a it's a Tuesday. Not a specific. I just realized we wrote Block Family members. She remembers. Um, it's lagging again. Okay, okay. It was lagging again, so I just disabled the camera. Is it fine now? Without the camera, we should be okay, right? I think so. Yeah, we came back to normal. Let's go. Okay, let's do this. Let's do this for like a few minutes without camera, and if it keeps going like that, I'll just disable it entirely. Um, yeah. So welcome back, everybody. We're going to be looking at pieces of code in our screen because code is beautiful. Beautiful as I don't know, as beautiful as the beautiful things get. Anyways, know that I have the camera disabled because the stream is lagging. If it keeps lagging, uh I don't know what to do then. Because yeah. Anyways, well, hello. And yeah, okay. No more time dilation. We have only 2 hours and 30 minutes because I have to leave at 10. Um, and thus, we're going to start with the stream. Let's go. So basically, we've been coding a memory allocator, as most of you know, if not all of you know. Um, Yesterday, we were working on our implementation of these key functions, one of them being partition block that allows us to partition a block, of course, and Malloc. Malloc being sort of the most relevant one out of the batch of functions we treated yesterday. That batch of functions being only one because it was Malloc, and we did partition block because it was needed by Malloc. So, yeah. Um, just to recap on the logic we have for Malloc, which it's a good exercise to see if there's any errors. We don't initialize our data structures in memory init, in init, mainly because we want sort of the user to not have to deal with the extra memory tax we impose on them if they don't want to use Malloc. So we initialize everything whenever the first call to Malloc occurs, right? So that is what we call lazy initialization. And what we do is we introduce padding so that the memory heap starts, in a practical sense, on an 8-byte aligned address. Then we create a ghost node. Then we introduce padding plus the ghost node size. And then we set up the ghost node to have sort of this information. And then we tell the red black tree that there is no root, the root being the left child of the ghost node. Now, we treat the size of the user to, instead of being the size, that they passed, it's an 8-byte aligned size. Well, not necessarily 8-byte aligned, but a size that, together with the header information, or at least the size information, is good enough, right? So that everything in total is 8-byte aligned. Now, we can treat this guy by simply looking for a free block in our red black tree. If there is such free block, we simply provide it to the user, right? We take it off of the red black tree, then we partition it in case it's really big. If it was really big and it was indeed partitioned, we insert the remaining piece back into the red black tree, but take with us the piece, sort of the leftmost piece, right? Now, whenever there's no free block, right, we need to calculate the expansion size of, like, how much do we want to expand the heap by, right? If well, given this expansion size, what we're going to do is we're going to go to the last block. If that block is free, there's an optimization we can perform, and that is, rather than expand the heap by however much we need, we can just reuse the space of the last block, since it's free, and expand by however much the number is, right? So if we wanted to expand by 20 bytes, but it just so happens that the last block is free and it's a 12-byte block, then we only need to expand by 8, right? So that's exactly what we're doing here. We detect if the last block is free, then we take a look at the last block, and if it is free, then we know that it has a size. We can, from that, compute the last block pointer, and then we can subtract from that last block size, from the expansion size, we can subtract that last block size. After that, we remove it from the tree. Why? Well, because we just changed its size, which means that it is going to be in a different position in the red-black tree. And as such, we definitely need to remove it, to reinsert it. Not only that, but we're going to serve it to the user so it cannot be in the red-black tree. Because remember, wherever you see the red-black tree, you need to think free block. So red-black tree is the representation, is the data structure that's storing the free blocks. So if you see remove, it means like this guy is about to be used for allocation, okay? Then after that, what we do is we expand the heap, and if the last block was free, that is, if we are to use that last block, we simply expand it. We tell it, oh, now you can occupy more space, right? Otherwise, it means that the last block wasn't free, so it means that the new sort of expansion size must be a block in and on itself, right? So what we do is we make the last block, the actual last block, be this new section that we just created, right? And after that, we set its size. We basically do all of the block operations. So we set its size, we set it to be free, and we set its previous free to be the correct things. After that, what we do is we say, well, independent of whether or not you reused some recyclable space, there's going to be a notion of a last block. Whether that last block already existed or it's the new expanded area, doesn't matter. We just know that the block that we want is the last block. And so what we do is we say, well, just grab that last block and give it to the user. But we have to be careful because if the block is too big, we need to partition it first and then give to the user the part that belongs to them. So that's what we're doing here, right? We partition if worth it. And if it was actually worth it, right, that is, there is a right block, then we simply say, well, reinsert that little guy into the tree because we're not going to use him. And after that's done, we simply return the pointer to the block, which would be, well, you got the lowest memory address in the heap, then you add the offset that is implied by a last block heap pointer, and then you add the size of size, right? The size metadata, because we want to skip this. This is the header of the block. We don't want to give this to the users for them to override. Okay? So that's all we did yesterday. I think the logic is sound, but as every single program in existence, there's always bugs. There's always something we get wrong. Uh, yes, like currently we have 7 eyes on the code. Yesterday we have around 30 eyes on the code at the same time. So gotta pay attention. Gotta pay attention, and hopefully we'll be able to finish Malloc today. By that I mean sort of testing it and seeing that it works correctly. How are we going to test Malloc? What a great question. The best way we can do it is simply using this sort of little file that we had created before. So we can simply create another function, which is something like test malloc, right? And what we are going to do is we have control of the heap. We made it 128 bytes. And then what we're going to do is we're going to call test malloc on this. And for test malloc, we're just simply going to do like a little toy example, right? So inside of A1, we want to store, some sort of string. So malloc, and then we want to allocate, say, I want to say 23 bytes, right? In those 23 bytes, we're going to store a string. So we're gonna call string copy on this. And we're gonna string copy into A1 the string that we want to store. Something like this is 23 bytes. Happy face and 2 exclamation points. That's 21 characters. So I think we can use the 23 bytes long and then an exclamation mark. And this is indeed 23 bytes, 22 characters plus the null, that gives us 23. And we should be able to see this change take effect in memory. Then after that, we want to allocate a second string. Now, perhaps a little bit of a longer one. So malloc, I don't know, something for 42. Thambjerg, welcome again. But yeah, welcome to the stream. Currently, we did like a little walkthrough on what we did the last time with malloc, and now we're trying to test it. Right, we're trying to see if our logic is completely sound. We're creating a toy example just to see if it like at least compiles and works. And after that, we need to develop sort of more important and like more actually well thought out tests. So yeah, that's mainly it. So we know that this is 23 bytes long. Oh wait, it's actually 42, and that I think is, oh, that's 51. Oh wait, it's 42. Are those 42 characters? Yeah. Okay, perfect. That is 42 bytes in total, including the null. And I feel this is a good toy example, right? Because it means that we'll be able to see an allocation of just 2 blocks, right? 2 blocks coexisting with each other, and we want to see how that goes. Yeah, okay. So we called this malloc. I think everything is fine. We can just compile Where is that command? There you go. Here it is. Let's compile this and let's introduce a little breakpoint over here. Right when we start the. So I don't want to run partition block since we do not want to sort of corrupt the heap before we start malloc. So let's introduce some breakpoints over here, and then let's roll with it. F5. All right. Let's try this out. So, oh, okay. 1, 2, 3, 4. Okay, we started the heap, and we want to take a look at these variables. There you go. So let's step a little bit. Now we know what the address of the heap is. So in our memory inspector, we can go to exactly that address, which is eerily similar to what we had before. The address that we want is that guy. So 0x12312311, then 100571B00. There you go. Then we're gonna do okay. So this is the address. This is the beginning of the heap. I want to try vibe coding assembly and then see what. Brother, do not do that. Do not. Whatever you. But whatever you do not execute the assembly. That'd be kind of fun though. If you want to like burn your machine to pieces, sure. Oh, whoa, 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 whoa. What just happened? We have some random pieces of information. 1E, 1C. Why did these guys appear? Huh? They just all of a sudden appeared. Okay. Oh, wait, no. This makes total no, actually it doesn't. Actually, it does not. I think I know the reason. We need to call mminit. We need to call mminit, guys. We need to, because this is meminit, which initializes the memory and everything. But this one is like, the malloc. Yeah. Okay. I think we're good. I think we're good to go. If we recompile once more, and then we run this, we'll hopefully be able to see in our memory tab. Oh God, they changed the address. Okay. 1, 2, 3. Okay, 7 zeros. 1, 2, 3, 4, 5, 6, 7. 1, 0, 0, 6, 5, 1. A20. And that's the full address. So we're gonna say, okay, right. So this is 10, 820. And everything is 0. Nothing should happen while we go on our call to malloc. Okay, the heap is intact. Then we execute mminit, should still be fine. And then we perform our first call to malloc. So in our first call to malloc, we're gonna allocate 23 bytes. What does that look like? Well, first, we should see some sort of initialization. So we should see this. First, the introduction of padding. And then after that padding, we should see the ghost node. So there is no padding, given the fact that this is already an 8-byte aligned address. As such, we should just start seeing the ghost node, which in fact could have just any sort of information, but we're looking for the left to be this huge number. Let's see. Okay, that sounds good. That actually sounds good. Are you a Linux enjoyer? I am. I'm not sure if saying that I am is the right word, because so I've used Windows my entire life. It's very popular everywhere. So when I was growing up, it's what I would use. And only like what? Around like the last days. So I finished my third year in college, right? And then I had like a little week or like week and a half to of just free time before I came here to San Francisco for an internship. And I had been thinking of like I don't like Windows, and developing in Windows is sometimes really annoying. So I switched to Linux. So I uninstalled Windows as my operating system in my PC, the one I have at my college apartment or like college house, and installed Linux instead. And it was so beautiful. It was wonderful. Really, really liked it. But yeah, so a Linux enjoyer, I would say so. A Linux expert, totally not. Like I am very far away from that. I do enjoy Linux though. Unfortunately, we cannot have Linux right now. My laptop is a Mac, and that's all we get. I think Mac is fine, but definitely like Linux a lot. So yeah, let's see, let's see. So over here, we are storing. Okay, okay. Does this make sense, people? Does this make sense? Because we have our struct for the header. We have it on the H file. There you go. So this one should represent the size, right? The size. So these 4 bytes at the beginning are the size. And the previous three and 3 flags. This is a 2, which means that this is a free block, which is true, and then its previous free is also true. We don't really care about the free flag since this is just the ghost node. Nobody's going to touch this. The previous free, though, that one we care about because it tells us whether or not the last block is free. So we just say yes. After that comes the left, which indeed is what we want, because when we initialize, let me see, let me see, let me see, let me see. Let me see, where is it? Where is it? Where is my memory? Okay. There you go, here. arbitrary.block. Over here, when we initialize this, we want the left of the ghost node to be the null H pointer, which is the max value a uint32 can take. And those are those FFFFFFF that you see. We don't really care about the value of right and parent caller because this is the ghost node. Those attributes don't apply to it. And so this is the right, and then this is the parent. So this whole row is completely correct, and it represents the ghost node. It is wonderful. I made a tile editor in my own UI library that was made in SDL, and now I'm making a version that replaces SDL with just Wayland. It gives me more control, but it costs my sanity. Yo, pretty cool. Pretty cool. You're gonna have to. Okay, once we go back to the hi Nick Vorsa, welcome to the stream. um, yeah, how are you doing today? Hopefully good, because today we're testing our Malloc. We're taking a look at the memory, seeing that it's doing everything correctly. We just started because yeah, yesterday we finished the implementation, so now we're gonna hunt bugs. But from here, you have to remind us of this when we are back to when I'm back in college, so that we can use the Linux PC. Because yeah, if Windows won't fix their OS, I'll just bring their OS to Linux. That is a great principle in life, you know. But yeah, you gotta tell us when you have finished that we can take a look at it on a Linux machine. But yeah, because currently, let's see, currently, oh wait, sorry, we lazy initialization seems to be correct, right? These are the flags for the size and the pref free and free, and a 2 means that it's both free and its previous is free, which is correct. Then after that, we have FFFFFFF, which is the left member of the ghost node, which should be an old pointer, which is the equivalent of, you know, the biggest value you can have. So that's an FFFFF. And we don't really care about what's stored in write and parent, so those shouldn't be modified. They remain 0. Now we have to go to the next step. So we have the size of whatever block we want to allocate, right? Size. And so currently, size is just equal to, okay, there seems to be something wrong because the block that was just allocated should have started here, right? But we don't see any information here. Instead, we're seeing like a random 1D over here and then a random 1C. There must be something wrong. So, oh, Tuna Fudge Phase, welcome to the stream. Do we have any reading material for this project or a starting point? So this was vibes based. Sorry, I feel saying that is really bad. It's really bad in the current era. By that I don't mean that this was what I coded. This it's just that we wanted to learn about memory allocators. So I just sort of watched a lecture on what a memory allocator does and what it's supposed to do and how it's supposed to behave. And after that, we took no reference. We simply created our design from scratch, how we thought the memory blocks should be laid out, and so on. Of course, we had seen a previous example, which was a very simple sort of design for the blocks where you only have the size and then it's sort of like a linked list of free blocks. But yeah, so we just started with that, with our own design, literally from scratch. And then as we went through it, we started implementing a bunch of stuff. And currently we are at one of the most interesting points where we have finally implemented Malloc after all this time, and we're testing and seeing if Malloc is doing the right thing. So yeah, I don't know. Oh, Fungiac says, because in the Wayland implementation, I draw the title bar as well. So I took Windows title bar look. I am also making the file dialog from scratch, so it looks like Windows 2. I'm not sure if I will ever finish. I'm not that good. No, I feel it's a good project to embark yourself on. It definitely seems very daunting. Like there's a lot of components to it. But yeah. So let's see. Here, when we are talking about the size and the align, yeah, I imagine there's a lot of details. It's anything related to UI, honestly, seems to me extremely, you know, I don't even know if I would be able to work on something related to UI. There's too many things to keep track of. But yeah, let's see, if size, so when we're talking about the size, we align it and we do all of that. Our red black tree is empty, so this should have been not true, which means we went over here, we expanded the size. So what is this current size of the heap? So mem heap size. It's 88, which seems to, the only thing I'm not bringing over is the lag. Yeah, that's awesome. Let's go. I mean, it's the only things you need to not bring back from Windows. Really good decision. So the heap size is 88, right? Because initially over here, where are we? Where are we? Here. The padding was 0. The ghost node size is 20, if I remember correctly. So currently the heap was only 20 bytes long. Why did it expand to 88? That's extremely suspicious. So I think we're gonna introduce some breakpoints here to see like exactly what's going on. And same here for the size and the free block and whatnot. So let's run this. Okay, Penguin Operator. Well, yeah. Hopefully when you come back, we have figured this out, why Malloc is not put in the blocks where it's supposed to. So the current heap size is 128, allegedly, right? But then when we call init, we initialize, our memory allocator. So we reset that to be 0. So the heap is 0. Now let's go into this call to Malloc. And what we have is the following. We have lazy initialization, right? We say, okay, if this is a first call, which is indeed the case, we're going to calculate the padding. Padding should be 0, yes. The ghost node size should be 20. Oh, 24 because it is aligned. Okay, that makes sense. After that, we generate this sort of expansion, which currently the heap says is 0. If we expand it by 24, it should be 24. Yes. And then after that, we tell the thing where the initial block is going to be. So that's the first one. And then we just set its left to be the highest value. So you should see a bunch of FFFs somewhere. Oh shoot, what happened? No. Oh wait, I'm looking at the wrong memory address because we restarted the program. So I think it's 006 2DA20. 2DA20. There you go. Okay. FFFFFFF. Perfect. Okay, that's good. We go to the next line. So now we calculate the size. The size that we asked for was 23. So it should be something like 24 maybe? 28. Okay. So now the new size is 28 plus the 4 of the header, that's going to be 32 in total for the entire block. We try and look for a free block, but we shouldn't find any. So free block should become null heap pointer. Yes, becomes the huge value. We don't find anything, so we go here to the expansion size. And so for the expansion size, we grab the maximum between the heap size and the expansion factor. The expansion factor is currently 0.35, so it should not be very big. The size of the header plus the size of this is 32, so maybe we expand it by that, or we expand it by 20. So this expansion size should be 32. It indeed is 32. We try and see if the last block is free. Now, remember, currently the heap is 24 bytes long. There is no such thing as a last block. And I think that's where the issue lies. So, okay, that is a bug. Because when we try to look at the last block, we should see no block, right? We should say like, oh, there is no such block because we have not allocated any blocks. But the ghost node is still there. And so this thing reads the information of the ghost node, sees that maybe the ghost node is free, and then it like utilizes its information for, because like currently its size metadata says 0 and 0. So maybe it's not going to interpret it as occupied, but if these little guys were like 1 1, or well, if the value here was a 2 or a 3, sorry, we would be in big trouble, right? Because we would see that according to the ghost node, the last block is indeed free. So this guy would try to use that last block, and that's just completely incorrect. So one thing we need to introduce is we need to set the previous free of the ghost node, because it's very relevant and important. We need to set it to be false, right? The last block is not free just because there is no such block. And we set the free of the ghost node to always be completely false. So the ghost node is never free. Perfect. So I think if we recompile this, good. I'm just going to get rid of most of the breakpoints until we get to this point in time. Same over here, because everything is working basically the same. I'm going to introduce a breakpoint only at that call. So let's run it again. Let's go. So we should be able to see everything working correctly, since now we marked the previous free as not free. So we initialize the memory with test malloc. We go inside of the malloc call. Yes, there you go. Let me now look at the memory and go to the actual address, which is 1005E5A20. Perfect. Okay. Awesome. So now we go through this process again. Ghost node size, remember, 24. Same for the padding. Now we set its left, so you should see FFFs everywhere. There you go. Then we should see the previous three to be false. So this guy should remain 0 throughout the execution of these next two lines. Ooh. Why did we change the left? Did you guys see that? When we went through the set is free, it changed this, which it should not have, right? Because the flags live in size. So there is a bug here. Let's see what's going on. All of the transformations take place inside SPFF. So this should not have affected that value. But for some reason it did. Some unknown reason. SPFF. Yeah, what's going on? So is free. Then we end this with this negation. Yeah, I think nothing should have happened there. If we step over, is it going to fix itself? No. Okay. That's a strange bug. Did we recompile? That should not have happened. Okay, let's see. We are in the heap. We go into Malloc. Perfect. We calculate padding, ghost node size, expand the heap. Here. So we set the left, and for this I need to inspect the memory. It should be 56561 AE0. Okay. When we do this, we should see FFFs. Yes. So this is left. This is SPFF, these 4 bytes. So when we set the previous 3, we only modify SPFF. So we should just see a 0, right? If I am not mistaken. So let's step into that function. Nothing changes, great. Okay, then we return back to the caller. Then we go to the next part of this function. And when we step into this, we execute this line, we shouldn't change anything. This one also shouldn't change anything, at least in the FFFs. Okay, it's probably this, right? There is some weird way in which we're accessing the next block. Oh no. Okay. So remember that the ghost node, okay, I see where the bug is. The ghost node is supposed to be precisely that, right? A ghost node. So it doesn't really interact with the tree at all. These functions, of course, are created thinking of a block that's actually a block. That's actually a block we care about that belongs to the tree. Because of that, whenever we perform these operations, especially this one, the set is free, we try and go to the next block to update the pref3 pointer of that next block. But this is the ghost node. It shouldn't have a next block, right? And so when we perform these operations, everything just, goes bad. So what we instead need to do is we simply need to set the pref3, right? Is3 should just not be messed with. I think there is also a sense of importance that I would like, something important that I want to highlight. And it's the fact that we're using these functions, right? A prerequisite for these functions is use it on nodes that are part of a regular. The ghost node is not one such node. So we're sort of cheating the system by using this. I think, although possible, it would be good practice to fix this BS, right? Just don't use the functions that, although they work, are assuming that you're inside a rem-like tree, because the behavior changes at some point in time, and then our entire program just, goes south. So I think for now, let's use them, sure, but we have to fix that in the future. Let me recompile. Let's go to the memory inspector again and run it. Okay, perfect. So we have the heap. Continue. So it seems to be a similar address. 5, well, no, it's actually not. 625 AE0. Okay, perfect. So now we enter Malloc here. So we calculate the ghost node size, 24. We make the arbitrary be the padding, perfect. We set the left so we see the FFFs. Now we set the previous 3. So the previous 3 should be a 0, so that 0 should stay there. There you go. So this is still 0, not a 2, not a 3, not a 1, which is awesome. Now we calculate the size, which should be 32 as we saw before. Sorry, 28 as we saw before. We try to find a free block, but of course there is none. We haven't allocated any. And as such, we skip this section to expand the heap. For the heap expansion, the value should be 32 if you just take the max out of all of these factors. 32. And then we try and see if the last block is free. This should be false because the red black tree, the prev free flag is currently false. Yes, it's false. So the last block is just a null heap pointer. We skip this section because we don't have a last block. Yes. And we expand the heap by whatever the expansion size is. Perfect. So now it's 56. Remember, it was 24 previously. We expanded by 32. Now it's 56. The last block isn't free, so we skip this. And instead, we make the last block become an actual block. So where does the last block lie? Well, we know that the ghost node occupies 24 bytes. There's going to be 16 over here. And then all up until 16, 17, 18, 19, 20, 21, 22, 23, and 24. So over here is where we would see sort of the last byte of that block. This should be the beginning byte of this new block. So we calculate where the last block is, and the value should be something like 24. Oh, last block is 56? Ooh, that is a mistake. Yeah, so I think this is just code. Yeah, this is code that remained from an edit we made, and we just forgot to change it. Because we need to we need to just enter the first byte of the expanded area, and the expanded area should just be whatever the last thing is. So the heap size, right? If the heap size is 26, I want to go to like the 26th byte of the heap, and then subtract from it the expansion size, so that I end up at the beginning of the new area we just created. Yeah. And then after this is done, we can continue doing whatever we were doing. Yeah, so let's do that. So let's recompile. Let's run this again. So today it's going to be a session that goes almost, all of it is going to be something like this, right? As we go through the Malloc logic and explore every branch. So we calculate the expansion size, this is fine. We skip this, we expand the heap, now it's 56, and now we enter here. So the last block should be 24, and the reason for that is, let me add a new view for memory. It should be 0x1234567 100 AA0. We want to see 4 megabytes into the future, perfect. So as we said, this is the last byte of the ghost node. So the new node should start here. And here is the 24 byte, with respect to the start of the heap. So last block should be 24 now. 24, perfect. Awesome. Hi, Penguin Operator. Glad you're back. Not much has changed. We have detected a few bugs, but they've been really easy to spot. So when we set the size, right, we want to set it to be the expansion size minus the header. That's going to be 28, right? So hopefully we see a 28 here, and then, after these 4 bytes take place, 28 bytes later in the footer, 24 bytes later, we see the same 28. So let's continue. And it seems like it happened, right? This is indeed the first byte. And I will assume that 1C is indeed 28 in hex. Let me just check here on my phone, since I don't want to open external applications, given that they make my computer explode. 1C hex to decimal. I'm pretty sure it is. Let's just verify. And yes, it's 28. Awesome. So 28 and then 24 bytes later. So there's 1, 2, 3, and 4. This represents the size. Then 1, 2, 3, 4, and then 16, that's 20. 21, 23. Ooh, 21, 23, 21, 22, 23, 24. And then the last 4 bytes, which would be 25, 26, 27, and 28, should represent the footer, which is indeed 28. So I think we have succeeded. This is a successful malloc allocation. Now, we set the previous 3 to be false, since the previous block is not, occupied. And that should make it, instead of a 2, so we set it to be 3 to true, because yes, this isn't. Whoa, 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 whoa. What just happened? Did you guys see that? We were just tricked. This was a 1C, which was supposed to be a 28. Now it's a 1D. Oh, but that's supposed to happen, yeah. Yeah, we're completely fine, right? We're completely fine because the pref free and the free are stored over here. So the fact that now it's a D means that the block marked itself as free. And then when we set the previous free, we should set it to false, apparently. So hopefully this guy changes to 0. Ooh, what just happened? So, interesting. So a value of 2 means that it is not free, but that the previous is free. Oh yeah, that's completely fine. Because we're saying, oh, this block is free. And so since this is the last block, it just went to the ghost node and told it, I am free. So the previous free of the ghost node should be true, which makes this a 2. Yeah, that's completely fine, and that's great. Now, we try to see if the partition is worth it. It should not, right? But let's just inspect the call into here. And Nekbol say, yeah, I see the emojis. Yeah, I'm happy too, you know. Oh, well, bug inspector. Yeah, that's a good way to put it. So we have the block space, which should be 32. Yeah. The size needed should be 32. Or 28, sorry. Yeah, 28. Then the total left space would be just the 28 plus 4, which is 32. And thus we should deem this to be not worthy. So then we skip and return nothing. Yes, perfect. So now there is no right block. We don't need to worry about it. So we skip this section and then we return the pointer. Which pointer should be returned? It should be the memory address 100609 AB, and then 9, no, not 9, AB 1 2 3 4. This guy should be the memory address that's returned. So adding C to this, not sure what it would be. Not very familiar with hexes, but I think we're fine. So if we go back and we take a look at A1, right? Once we perform the string copy, oh yeah, there you go, add C to it. So ABC, AB plus the C, and then we're exactly here. So when we write the message, we should be able to see it expand or like, use all of this space except for this one, which should still remain 0. Yo, let's go. And this one is the null terminator of the string. So this one is 0, and then the footer is still fine. And I think you can take a look in the right and see that, oh, yeah, oh yeah, there you go. And see that the message is there. This is 23 bytes long. Yo, let's go. That's awesome. Okay, so I think that one's perfect. Now we're going to see what happens when once we have a block in memory, we try to allocate a new one. So we're gonna allocate 42 bytes this time. We enter this part. Now, Malloc was called previously, so lazy initializations should not kick in, and thus we should skip this section. Yes. The size. So currently it's 42. And 42 plus 4, that's 46. That's not an 8-byte aligned address. An 8-byte aligned address would be 48, and thus we should see the size change to 44. Yes, perfect. Now we try to find a free block. There is no such thing since, we haven't freed anything. And so we skip this section. We calculate the expansion size, which should be, let's see, 35% of 56 is definitely not enough. So it should be 48. Indeed, expansion size is 48. Now, if the last block is free, which is not the case, so we should see this become true. Sorry, false. Ooh. Ooh. Oh, we have a bug. We have a bug, people. We have a bug. See how when we enter. Oh, morning sci-fi. Thank you very much for following. Yo, we have a new follower. But yeah, so notice we have a bug here. We have a bug because when we convert the expanded area into a block. Oh, wait, welcome to chat. Thank you. Thank you for hanging around. But notice we have this bug, like when we expand the heap and we convert it into a block, we set that block to be free, which is fine because we haven't allocated anything yet. But we forget to set it to allocated when we return it to the user. So actually, this thing should be false, right? Because that's why the last block is free, because we set it to free and then we completely forgot to set that bit back. And so now the program thinks that that thing is free despite containing user data. Okay. So we know that this first part is right. So I'm just going to skip that and let's just start at the second allocation. But first we need to recompile. Perfect. Let's run it. And once we run it, we should be able to see where the heap is. So let's go to our memory inspector. Let's delete this view and add a new one and have 0x1234567 1005 A1 AE0 and then 4 megabytes into the future. Oh. Hello? Oh, yeah. So this is the malloc code for the first allocation. After all of this, we kind of know what the state should be. FFF, yeah, and the size and everything. So these guys, all of these first 4 bytes should remain 0 after all the things that happened here. So we set the size to be something, yes. We set the free to be false, so everything should remain 0 over here. And then it remains 0. Yes, perfect. There's no need to partition since the block is just the right size. And then we insert this into the regular tree. Finally, we return the pointer to the user. Perfect. We write something and we see it appear, and that indeed appears, right? This is 23 bytes long, and that's what memory says. So let's go. Now we move to the second allocation. So hopefully everything is right. There should be no lazy initializations, and this is the second call, not the first one. Then we go here to the size, right? And we calculate the size. The size should be 44. Yes. Now we try to find a free block, but of course there's no free block since we haven't freed anything. And indeed, it is the FFF value, which is equivalent to null pointer. So we skip this section. Then we calculate the expansion size, which should be 48. Yes. Now we see if the last block is free. We haven't freed anything, so that should be false. Perfect. And the last block should be a null heap pointer. Okay. Now we skip this section since the last block isn't free, and we expand the heap by 48. And that should give us like 104. Perfect. This we skip since the last block isn't free. And then we convert that new 48 byte area into a new block. So this entire area, which starts 1, 2, 3, 4 over here, starts in this byte. We need to let me scroll a little to the side. We need to start here. So the last block should start at byte number 56. Yes, last block 56. We set its size to be 44. So pay attention. 2C. Is 2C correct? So it would be 2 times 16, which is 32. And then the C, which is 12, I want to say. Yeah. So it's 44 indeed. Now, we set this to be free to false. This is the last block, so we should see a 0 still here at the beginning. So all of them zeros. Perfect. Now, we set the previous one to be free as false, and thus nothing should change. Perfect. Let's go. We enter partition if worth it, but we should receive nothing because we don't want to partition this block since it just fits us right. Yes, right block is indeed a null heap pointer. And then we skip this section and then we return it to the user. Awesome. Now we go here and we copy a message which should span all of the 42 bytes, except it should leave these three guys as 0. This would be the null terminator. This would be just the 2 that should be left untouched since we changed the size from 42 to 44. So these memory addresses should not be touched at all. Oh, sorry, no. No, actually, no. What am I talking about? The size should disappear. This thing over here should disappear. So it should become like some weird value. Yeah, okay. 2C changed completely, was obliterated, and then the null terminator was introduced, and then the 2 extra bytes that we didn't touch at all because they were added just for the sake of padding. And thus, we are a byte aligned for the next block. People, we see the message on the right. This is 23 bytes long. Oh, wait, it's 42, which is indeed the case. 42, including the null terminator. People, I have disabled the camera because the stream gets laggy, but let me turn it on for a second and see if anything weird happens. So if it lags, let me know. But this is worthy of celebration. This is worthy of celebration. Because we have effectively performed our first allocation with our own version of Malloc. And it works. Which I'm very happy about. And I hope all of you also are very happy. This is something very important. We did it, people. We did it. I mean, it's a two example, right? Like there is hundreds of bugs yet to be discovered. It seems like the logic when it because currently we're not freeing anything, so we're not using the red black tree at all. Imagine the amount of bugs that are gonna be introduced when we actually start using the red black tree. We tested the red black tree before, but things are gonna happen when we. So I think this implementation of Malloc is correct as far as the toy example goes, which is just allocate blocks and never free anything. As such, it's just good enough, right? Uh, Morning Sci-Fi, and congrats. Thank you. Thank you. But how many lines of code? Last I checked, the version of Malloc I had laying around was around 5,000 lines. Damn. Okay. We currently have not that many. So we have the main file, which is 245 lines long, but notice we haven't implemented free or realloc yet. Um, then yeah, I imagine too. There may be a lot of hidden edge cases or something like that. Most of the content is in the red black tree file, because it's like, as you can see, it's like a very long file. 362 lines, not very long, right? But compared to the main file, 362. Actually, let's add them up. That's a great question. I want to know how many lines we've written so far. We haven't written that many though. So we have, let's see, 245 plus 362 plus maybe the header files count too, plus 89 plus the header file of the red black tree, which is 81 plus, oh wait, it's 777 lines. Exactly. Like these files are 777 lines long. If we include the little library that we've been interacting with to sort of interact with how the key works and everything, it's a little more. It's like 178, and then whatever 13 is, 878 plus 3 881 plus then 891 lines plus the 4 lines of here 895. So yeah, we are very far away from 5,000. It is a lucky number though. Yeah, it's 777. So I don't know. We'll see what happens. So yeah. Okay, people. I think. Ah, I'm sure there are minimalist mallocs that are way smaller though. I imagine so. I think someone in the chat in a previous session, I think it was Strignit or Andrew, one of the two, shared a memory allocator was like 200 lines long. I didn't want to read the code because, right, we want to be fresh and everything, but it was 200 lines long and it was coded in Zig, which I don't see how you can make it in 200 lines. It must have been really simplistic or minimalistic, but yeah. I mean, once again, I haven't taken a look at the code because I just don't want to bias myself. But we'll take a look after we finish. So yeah, let's see. So guess who's back? I can't believe I showed up at such a pivotal moment. Yeah, we've been working on this for like what? Actual time 2 weeks, I think. Not actual time, sorry. Like, you know, time if you measure it from the exact moment we started, which is 2 weeks ago. We started on the 4th of July. Effective time, it's been more like 5 days, right? Because I've had to take long breaks because of all the responsibilities. But yeah. So it is indeed a pivotal moment. So it's kind of interesting. Yeah. Okay. So. So currently, I think this deserves a prize, and the prize we get is pushing this to the GitHub. Git add, git comment dash m. Then we're gonna say fix sort of fix bugs in Malloc. So I think we're gonna implement a fix, and then we're gonna say Malloc. Actually, I don't know why we're calling it Malloc. Like, let's just call it Nalloc, which is the actual name of the project. Fixing Nalloc's code. After fixing Nalloc's code. Allocate no free path seems correct. And let's just push that. Perfect. All right, we have it. Malloc rewrite. And I think that from what I can see, I think we can just um yeah, so we can focus on the free now, which is the next part that we need to implement. But also, give me 1 second. I am looking. I forget. When you do git merge, you do it. So we're gonna check out into main. Yes, and then we're gonna merge the branch, which was the refactor malloc rewrite, if I remember correctly. Git branch. Yeah. So we're gonna merge into. We're gonna grab refactor malloc rewrite and merge it here. I think that's the syntax. I don't remember if you are placed in the main branch and then merge the refactor, or you are in the refactor and merge it into main. So let me look at the git merge syntax. Uh, sorry about that. It is, let's see. Da-da-da-da, merge a branch into your current active branch. Okay, perfect. So git merge, refactor, malloc rewrite. I think this is right. Perfect. We did it. And so now we can actually push this merge. Well, actually, did we merge? Yes. Okay, perfect. Awesome. Let's go. Okay. I think everything should be in the GitHub now. Just keep free and provide 100% guarantee on memory leaks. All right. Well, the perfect allocator for Microsoft. Anyways. Yeah. Anyway, I don't know why we're throwing so many jabs at Microsoft today, but uh, if somebody works on Microsoft, please don't be offended. This is, we just like joking around with it. Um, yeah, let's change the name of these functions. Actually, I don't know why we've been sticking to the mmmalloc. I think I just want it to be Malloc, which is the name of the project. So Malloc. Oh shoot, no, Malloc. Then let's switch to the header file and name this Malloc also. Yeah, so I think perfect. Oh wait, I see that. Ooh, I think the stream was lagging, right? Okay, I disabled the camera because I think it was lagging. I'm not sure what's going on with the camera. The camera just like immediately when you enable it, it destroys the entire stream and makes the bitrate go uh like up and down like crazy, like a roller coaster. Anyways, so we need to update our tests to use that call. So now it's malloc, perfect. And this is actually the malloc we want because we have like a toy heap that we're gonna use. Perfect. Okay, awesome. We have implemented it. Yay. Now, people. Now we proceed to free. Let's go. Yay. Who's excited? Me. Anyways. So free is gonna impose a little bit of challenges, right? So one of the first challenges, and it's something that I noted in the to-do so that we wouldn't forget, is that we need to reinstate metadata, right? What I mean by that is, if you remember, I'm gonna go to the Excalibur back to for this, right? Let me hide this panel, which is annoying. Well, sorry about the organization. Currently, after all of these days, all of the drawings have become a little unhinged, but yeah. So let me erase some of them. What we currently have, this is the current design of our blocks, right? Remember that when we provide a block to the user, we let the user overwrite all of this information. So I think we should actually update the design. This is no longer user data. This is more like padding data or like extra data needed to accommodate the user's request. I'm just going to call it user data because that's what we've been calling it. But just know, this is what a block looks like for us. This is the design we landed on. And we yesterday decided on an optimization thanks to Negvosa that was, okay, what happens if we, so basically, we keep track of this metadata for a reason, right? The reason is the red-black tree. So we keep track of a left pointer, a right pointer for the children, then a parent, and then a color. That red-black tree is the data structure that's storing our free blocks so that we can look inside the red-black tree and try to find a free block that suffices the user's request. But when we provide the block to the user, we remove it from the red-black tree. So all of this metadata no longer makes sense, right? Because it's no longer in the red-black tree, so we don't really care about it. Right? We just gave it to the user. It's not like we're keeping track of anything over here. And thus, we can give to the user a pointer to here. So they can override whatever they want from that information, right? They can do whatever they want with it. And the same thing happens with the footer. You may be saying, sure, but don't you need the footer so that whenever you have, okay, look at these lines. Anyways, so that whenever we have a block that's allocated and another block that's allocated, right? If you free the block on the right, then he's going to be fine, right? But if you free the block on the left, then coalescing should take place, where I look to my right and see if that block is free and then merge them together, right? And so the reason why we have size in the footer is because if it happens that both are allocated, then this one gets freed, and then this one gets freed, this guy wants to take a look at its left neighbor and see, are you also free? The problem is it wouldn't know how much data it should skip to get to the header in order to know that information, because user could have allocated as much memory as they wanted. So we just include the size here so that this guy knows when to jump or to what place it should jump to. But remember, this size metadata is not needed when the block is allocated, right? If the block is allocated, this guy doesn't really need to know the size of the block. It just needs to know, are you free or are you allocated? If you're allocated, I don't really care. If you're free, I do care and I want to jump to the header. For that reason, we have stored a bit inside the header of every block that's called the previous free bit. The previous free bit, what it does is it says, is the block right next to my left free? And so now this guy doesn't need to take a look at the footer of the previous block to know that information. And thus it means we can give that footer to the user. So the user can not only use this metadata to store whatever information they want, they can also use the footer. You may be saying, sure, but if we get rid of the size here, once the block gets freed, right, how are we going to let the block on the left know how much it needs to jump by? Excellent question, my dear child. What's going to happen is when we free the block, right, when we free the block and all of this is written by the user, so it could be just random data. When we free the block, we are going to reinstate the metadata that we need. So the user is going to give us the pointer that we gave to them. From that pointer, we can just go back a tiny bit to get to the size. So we're going to be aware of the size. Once we know the size, we're going to jump to the back in order to reach the footer, reinstate the size so that if another block gets freed and they realize that their neighbor is free, they actually see the size in the footer. And we also reinstate the whole left, right, parent column metadata, right? So that is the plan. It's sort of state that's only needed when the block is free, and thus once it's allocated, we forget about it and reinstate it only when the block gets freed again. So that's what we talk about here when I say we need to reinstate the metadata. Not only that, but we need to apply coalescing. I think this is the way you write coalescing. Let me verify. Once again, English, not my first language. So let's see. Coalescing. Oh, coalescing is written with a single L. Yeah, sorry. So it's a single L. My bad, guys, my bad. Okay. Coalescing. Perfect. So we need to implement that logic of that I mentioned earlier. If this block gets freed, it just looks at its neighbor and says, "Are you also free? If so, let's merge together." Right? It's like fusion. Right? Okay, perfect. Do we need to do anything else with free? I mean, of course, after the coalescing, we need to add to the red-black tree because the red-black tree keeps track of the data structure. Set the pref free on the next block. Oh yeah, I mean, yeah, set the free flags. So currently our block set is free function already does the pref free work for us because it goes to the next block and it sets the pref free. So that's great. And in fact, we should replace this with set pref free. So I think here, if we just do bk set pref free. Oh, sorry. There you go. bk set pref free of the next block to be is free. bk set pref free of next block of my block and make it be is free. That simplifies everything a little. All of these functions are hopefully going to be inlined, so don't worry about the fact that we're calling like 20 functions per function because the code is really small, right? So it wouldn't affect our instruction cache or anything like that. And they're used so often that it is a benefit for us to inline them. We'll just worry about that later. But for now, so this function already takes care of those flags. So yeah, let's just tag that as setting the free flags. And after that, we don't need to return anything to the user. So that's fine. Yeah, I think this is the grand scheme of things. So perfect. Okay, so first step, we need to reinstate the metadata. How are we going to do this? So remember, the only thing we have is the pointer that the user gave us. And that pointer points to this part of the block. So points to this part of the block. Okay? And thus, we need to go back by 4 bytes, which is what the size is. So let's just do that. We're going to create a heap pointer to the block we're talking about, which is just going to be this thing, the pointer that they provided, minus the size of a uint32. Right. So we're looking at the pointer to that block, and from it, we need to make this a uint pointer type. From it, we subtract the first address of the heap and heap low. And thus, we obtain the heap pointer to the block we're looking at. Right? Perfect. I think that's 1, 2. Let me think. Yes, perfect. So once we have a heap pointer to that block, we can just do whatever we want, right? Because we're just gonna reinstate everything. So we set the size of this block to be whatever the header has. So it would be block header. BK header of my block, and then I want to access Oh, we cannot access the size directly. I think we can just do BK size of my block. Since we already know that the size is definitely there, we can just use BK size, right? I think it is important to include in the doxygen van free. Assumes header is well formed. And then here we need to include a remark that says obtains size from blocks header, not footer. Okay, perfect. So it gets it from the header. Then we set that to be the size, and set size sets both the header and the footer. So that's the way we reinstate it. We also need to set the left, the right, and the parent, but those will be set by the red-black tree when we perform the insertion. Since the red-black tree doesn't really assume that there's any useful values in there, we can just not set them. Same for color. And from right, left, parent, color, size, we need to set the current free and the previous free. So bk set is free. Who is free? Well, my block, and set it to true, right? And also set the previous free to be what? So I would need to know whether or not. Ooh, wait. Actually, no, we don't need to set the previous free because that guy remains. So something important, something that we need to remark. No need to set prev free since it is part of size. It hasn't changed, we didn't change it. Or I feel this is more explanatory. So there's no need to set previous free since it's part of size. By previous free, I mean from the block that was just freed, we don't need to modify its previous free because that lived in size. Size is completely unmodified. And previous free is something that doesn't concern us. It's something that relates to the block that's right next to us. So there's no need to set it. It's already in its good state where it should be. Okay. So I think those are the flags we need to reinstate. After that's done, we can be happy about it. Rhyme and sunshine and rainbows and all of that. I think that's all, right? So now we need to perform the coalescing. How are we going to perform the coalescing? Great question. Great question. So we're going to look at the next block. So first, coalesce on the right. So if the block is free, which block? Well, my next block, right? So if the next block to mine is free, then what I want to do is I want to merge with it, right? So merge with right block. Or better, coalesce. I think this is the way you write it. Let me verify it. Is this the way you write coalesce? It's like such a strange word, but it's so beautiful, It's like one of those words that you look at it and it's like, wow, coalesce, right? Sounds very classy. So we'll see. Enable the camera so hello everyone. Let's see if it stabilizes. Not sure. If it goes down, then I'm just gonna turn it off again, and then we go on a cycle like that. I need to fix that, I think. I think the problem is the laptop itself. I don't think it's able to support as much workload as that. Anyways, we coalesce with the right block, right? Otherwise, the Sonny boy is like, wait, what is it? Wait, does Sonny mean anything? Am I missing something? But yeah, thank you. I mean, I know most of you come here just to see this beautiful scene. But, anyways, coalesce with the right block, right? And then we also take a look at the block to our left. So if the block to our left is free, so if Micktoons. Ooh, thank you for following Micktoons. Yo, let's go. I have another follower. And yeah, we're coding a memory allocator from scratch. We're currently implementing free. That's the context of what we're doing right now. So let's see, guys. So we have the block is free. We have then the next block is that. And now we need to check if the previous block, so like our left block, is free. Mixins is very cool. Thank you very much. Yeah, you feel free to hang out around, to share your opinions. Let us know what you want. Maybe there's something that we do wrong or something like that. Have no fear of asking questions also, because everyone here is learning. I did not know what memory allocators did before starting this project. So yeah, we're just learning by doing. But yeah, okay, so here we're looking at the block to our right. That's completely free. But to look at the block on our left, we're gonna have a bit of trouble. Because remember, if the block on our left is allocated, then all of this data is gone, right? So first, to tell whether or not the previous block is free, we need to access the isPrev free data. So I think I'm surprised that we haven't implemented this function. I think we actually have, no? Yeah, block per free. Oh, I think it's just not in the header file. So let me just. Well, yeah, the camera lags everything down. I'm not sure why. Okay, let's continue like this. We can turn it on later. So I think the problem here is we have not put it in the header file. So we have is bk size, bk set size. Then we have an extern bool bk prev free, and then we set the heap pointer to the block to exist. After that, we have a void for the block to set the prev free flag. Right. So we have the heap pointer t and then block. Oh, and we also need the value by which we want to replace it. Perfect. We set its size. We set the left. We set the left. The right. Then the parent, color, and then the is free, and then set is free. Yes. Okay. Everything's fine. And so now over here, yeah, if the block previous to us is free, which is information we store in our block header, we coalesce with the left block, right? And that should be the coalescing logic. Notice that it is possible that both of them are free. So then we coalesce with the right block, and after that we coalesce with a left block. And it is a very important distinction, right? Why? If we coalesce with, so I'm saying that the order here matters. So coalescing. I'm going to include an important comment for us in the future, which is this, right? Order matters. Why does the order matter? Because if we have two blocks, right, side to side, so suppose that the one on our right, which is this one, is free, and the one on our left is also free, and we are allocated, right? If we get freed by some, routine of destiny, if we take a look at our left first and coalesce with the left block, we're gonna have trouble. Because when we coalesce, the header is now this, right? This, this block is going to become this whole thing. And so now the header is just this guy. But we are holding a pointer to this block, right? If we do the coalescing first with the right and then with the left, things are going to be much simpler because with the right, we are still the header. And then with the left, maybe the header changes, maybe it doesn't, but at least we don't have to worry about it while we're coalescing, right? Those left-right blocks, if they are free, they are in the tree, should we remove them before merging? Yes, excellent observation. Like, yeah, it is part of the logic that we need to implement here. And yes, we need to remove them before merging. That's a good observation. So when we coalesce, let's do the right block first. So when we coalesce with the right block, what do we need to do? Well, first, we need to identify what that right block is. So what I'm going to do is, let's just, create a heap pointer to the next block and just be like, next block, and then my block, right? Notice that we have a problem, right? And it's that I think the next block function, yeah, there you go. The next block function is being used for nasty purposes. So here we perform this optimization, or not optimization, this sort of simplification of thought. And it's the fact that we said, well, we store the previous free information in the block that's next to us, right? So to know if we are free, we take a look at the next block's previous free pointer, and then we realize that fact. The problem is when the last block needs to know whether or not it's free, it doesn't really have a next block, right? There's no such thing as a next block for him. And as such, we determined that the next block of the last block was going to be the first block. But that is a little confusing, so we just made it be the ghost node. The problem with that is that for the sake of coalescing, this is going to be really bad. Because if we try to coalesce with the last block, then we're going to coalesce with the ghost node. And then we're merging together two things that are not even contiguous in memory. You could say, oh, Sharif, we simply make the ghost node never be free. But that seems more like a hacky approach rather than the correct approach. I think we should make the function do what it is supposed to do and make next block return no heap pointer whenever there's actually no next block. And we can, whenever this thing is used, just, set it to what it needs to be. I think next block is only used in here. So yeah. So next block is just there, and then same with this. So I think we should be fine. So I'm gonna delete this, right? And instead say, well, right, we have a special case. If the block we're talking about is the last block, which is this condition, is the last block, then we're going to set the previous free of the ghost node to is free. And then otherwise, otherwise we just set it to be the next block of whoever we're talking about. Right? I don't like else's. I'm very sorry. So I'm going to introduce a return here. And then, yeah. If this is the last block, the ghost node contains its spread free. Perfect. Okay, that should do it. And so now we can simply make next block return what it actually should. I'd have to say we still need a branch here where we say, well, if the block plus the size of boolean32t plus the block size of that block is greater or equal to the last memory address, then we need to return that it's a null heap pointer, right? Yeah, okay, perfect. So I know. We could do this branchless somehow, maybe by multiplying some conditions with something else. But let's not do that right now. Let's just keep things simple and have a good thought process and good logic. Once we are strong with the logic, we'll be able to perform optimizations. Okay, but first we need to have a good mental model of what's going on. Okay, all right. Look. So when we are talking about free, right, when we coalesce with the right block, we want to know who the next block is. And that is something that actually we should do here. So we have a heap pointer to the next block, and we make it be the result of the next block function. So we grab the next block of this block, and then we say, okay, are you free? And the reason why I separate it and put it outside is because we also need to check whether or not that block exists in the first place. If n block is different from null heap pointer, and this happens, then we do things. So it is very important and relevant. I know it's kind of boring, but let's include asserts that verify that every block that we're passing to this is not a null heap pointer in every single function that we're talking about. Just so that it catches mistakes if they ever happen. Oh shoot, wait. Okay, Control V. Set the block and then the color. La 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 la. Perfect. And then we set the parent. We also need to verify that. And we have the parent. Da 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 da. And then we set the right child. Then we take the right to. We assert that it's not null. Here we assert that it's not null. We also assert it's not null. Assert, 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 and assert. Perfect. So now we go to free. Yeah. If this thing is not a null heap pointer and the block is free, then we coalesce with the right block. This guy will never be null, so we're fine. Okay. When we coalesce with the right block, right, what is it that we want to do? So we want to do a couple of things. First one, of course, check if the right block is free, but that's already given. We know that it's free. So we remove the next block from the red-black tree, right? After removing it from the red-black tree, we merge the blocks together, which is hopefully a simple operation. And once that's done, not only do we remove the end block from the red-black tree, but we also need to remove the current block, but the current block should not be in the red-black tree. Right, so one thing I think is important to do is to assert that whatever block you're giving to me is a block that is not free. Right? Perfect. So now what we're going to do is we're going to say, well, coalesce with the left block. Right. Sorry, not the left block, the right block. We remove the next block from the red-black tree. We merge the blocks together. And once the blocks are merged, we simply, we reinstate, fixed metadata. especially we need to set the pref free, especially set the pref free of the next block. I would argue that since the next block was already free, there's no need to do this. So let me ask 2 question marks for that. There is no other type of metadata that we need because size is fine, current free is fine. Just make sure that the metadata just doesn't really change. So reinstate it just to make sure. And once that's done, we just reinsert it into the red black tree, right? Into our tree. Then once that's reinserted, we should be totally fine. I am willing to say maybe we don't reinsert it. We move that step to later. Maybe asking why. The reason is because we're also going to potentially merge with the left block. We don't know yet if we're going to merge with it, but we could merge with it. So it's better to insert into the red black tree the final block that we're going to have after this, rather than insert here and then realize that we also needed to merge with the left. So now we need to remove it from the red black tree, modify it, and reinsert it. Because remember, deletion and insertion from a red black tree, data structure to store the free blocks, is the most expensive operation in a memory allocator. Okay, so we want to avoid those as much as possible. So we coalesce with the left block. And for the left block, the logic is going to be just exactly the same. So one thing that I do want to do is we could just export this behavior to be a function. And the reason is because left is also going to basically be the same thing, right? For that reason, and also for the reason that I forgot. Oh yeah, because from a function we can return the new pointer to the head of the block. So if we merge it with the left, right, we simply make it so that the interface sort of forces the function to return the pointer of the new header, and that way we don't have to worry about, oh, where is the header or whatnot. We just trust the function to provide us that. So let's simply go over here. So these are sort of Malloc related guys, right? Over here, I want to include the free helpers. So let's do. Oh well, I guess the block manipulation section already fits it pretty well. So let's just do that. Every single time we coalesce, we're going to return a heap pointer to the new block that we just created. So we're going to call this coalesce blocks. So to coalesce blocks, what you need to pass me is, well, who is the first block, right? So let's call this block 1, and then who is the second block, right? Block 2. So it is important, right? We're going to have here in our preconditions, block 1 is to the left of block 2. Okay, we impose that order. And of course, we're never going to remember that that has to be the case. And so we guard ourselves with an assert. We're going to say, well, assert that for block 1, the next block is equal to block 2. Right? That's the way we can check. And of course, block 2's previous block is hopefully block 1. Not only do we need to assert that, but we also need to assert that both blocks are free. So block is free for block 1, and that the other block is free as well, block 2. Right? Perfect. And so now what we're going to do is we're going to say, well, if we know both of those are free, gotta go. See you later. Oh, Penguin Operator, it was nice seeing you. Have a nice day. Yeah, thank you for joining the stream. Yeah, hopefully you come tomorrow to a lot of advancements. But yeah. Okay, so we assert whether or not the first block is free, then we assert whether or not the second block is free. Both of them must be free. Once we've verified that, we check that they're right next to each other. And I think those are all the conditions that we need. Select block 2, and both are free. Right? Both are free blocks. Do we need any sort of different precondition? I think not. Right? I think not. Yeah. So now that we have this, we need to coalesce both blocks. Yeah. So what we're going to do is we're going to block 1 is not yet free. Well, we need to, like, that would be more of an issue of the caller. Like, when we call that function, would need block 1 to be free, right? It's like the contract that we establish with the caller. Both of them must be free, because if one of them has user data, then we would be coalescing two blocks, that are not free. I guess we could consider the realloc case, where maybe you can expand by some amount, and it just so happens that the block to your right is free, and thus you just coalesce two blocks. I guess so. I guess if we are thinking about realloc a little bit in advance, we can just assert this. For now, what I'm going to do is this, right? I'm going to include this assert still to assert that block 1 is free, but include a comment for realloc. Make sure to change to not check whether block 1 is free, right? And rather than warning, this is more like a to-do. So the reason why I do this is because when we're coding free, the scenario should be that block 1 is free. Is a free block, it just doesn't contain data. Block 1 is coming from free, it's not yet free nor in the tree. It has the free bit set. It does, because here was where we set the is free to true. So that's what I want to be checking here when we perform the coalescing. And I'm just gonna include it there because this is the right mental model we should have for free. So I want this to flag whether or not block 1 is free if we ever do it with a block 1 that's not free. I want that to crash the program so that we know this. So I'm just gonna include it there, and then for realloc sake, we're going to delete it, right? Once we have verified that free works. So we assert those two. And now that we have all the preconditions in place, what we want to do is we want to merge the two blocks together, which should be a simple task. So first thing, we need to remove... Okay. I see a problem. Yeah. We have a problem here. So maybe not also this is what you're referring to, although I think... Okay, you've talked about something similar, but not exactly this. But yeah, we're gonna have a problem because what I want to do next is remove them from the red black tree, block 1, and then the same for block 2. Block 2. The problem is gonna be, of course, that like block 1 is not yet in the red black tree, which I feel it goes to something that Vorsa was mentioning. I think we can nonetheless get away with this. But it would be better if not. So can we somehow, maybe we can add as a precondition that both blocks should be out of the red black tree, right? I think that's fair. Yeah, right. So maybe I think something we can do, something we can start doing. This is going to be an important decision. Look at me in the eyes. Important decision. So the important decision is we sort of encounter it ourselves frequently in the scenario where the fact that being free is equivalent to being inside the red-black tree is a troublemaker, right? The fact that we've made the like this sort of connection that like free means you are inside the red black tree has generated multiple problems as we've been coding, right? Because remember that multiple times I've been saying like, no, we cannot do that because being free is the same as being in the red black tree, and so that notion blah 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 blah. So I think we need to decouple those notions. We need to and it is the right way. It is the right thing to do. We need to, in our mental model, simply separate them. The red-black tree stores free blocks, and that's the only thing it stores. But a block being free doesn't imply it being in the red-black tree. So this would be, instead of an if and only if, it would be as an if, right? If you're in the red-black tree, then you're free. But if you're free, that does not necessarily mean you are inside the red-black tree. Okay? I think it is a reasonable enough thing to do, and also easy enough. We just impose a little bit of more sort of memory weight on ourselves, because we now need to say, okay, if I'm going to insert into the red black tree, this thing better be free. If I'm going to remove from the red black tree, then I need to set this to allocated, right? And stuff like that. As such, I think it is the better change, in my opinion, because the red black tree being in charge of the freeness of a block seems rather cursed. Like, it has been damaging all of the progress, and like I know we could technically just remove it from the red black tree. So this is the situation, right? If before calling coalesce, we remove them both from the red black tree, there's going to be the problem that since the red black tree for some reason is occupied with setting the free bit to false, it means that when I remove them, it's going to set their free bit to false. And so when I go to coalesce, it's going to be telling me that I'm coalescing two blocks that are actually allocated. And so that thing should make coalesce complain and crash the entire program. But of course, that's not the case, right? So what I'm saying is because of that thing that the red-black tree carries the free state, we cannot differentiate between the case where we have two free blocks that, despite being free, are just not in the red-black tree because we're going to transform them, and the case where you have two blocks that are allocated. That is like very dangerous. Like, that's something that we don't want the program to have a confusion with. So I think decoupling that notion is, if anything, the best decision we can make. So let me see where all of these things happen. This happens when we return, then return. Okay, I think we can simplify all of this logic. So yeah, we just get rid of all the BK set frees. Set is free to just be, so whenever we call arbitrary insert, which if I remember correctly is a single place in the code base. Actually, two places, apparently. One would be, oh wait, no, it should be two places, yeah. One below this one. Yeah, okay. So when we insert something in the red black tree, we need to make sure that it is free. So what we're going to do is we're going to say bk set is free, and we're going to call the right block block to be true, right? Yes. And then here we're going to say bk set is free. Then we're going to set the right block's free bit to be true. Yes, it's free. And those are the only two calls that we have, so that's completely fine. And now for remove, we need to make sure that after we remove it from the red black tree, we set it to false in the places where it matters. So here, let's see. If there is a free block, then we remove this. We remove it from the red black tree, and then we set it to false. Oh, sorry. BK set is free for my free block to no longer be free. Right? And then over here, the thing we do is, well, the last block we remove it from the red black tree, right? But actually, this is one of the situations where, for example, we can use this, right? After we remove it from the red black tree, we still want to think of it as a free block, because this is the last block, the one that we modify to expand it. So we still want to think as a free block, and thus we simply remove it from the red black tree. And no need to set it to occupied, right? And so, because that we do later, right? Set is free to false and all of that. So I think these calls are fine, they're correct. And over here in the red black tree code, we simply get rid of whenever we insert setting the is free bit, and we changed it to be an assertion, right? Assert that whatever you're trying to insert is always free. So bk is free, the new name, right? Perfect. So we assert that, and I think it's just the C++ extension being really slow. Macro assert. BK is free. Oh yeah, it's still loading. You can take a look at it here. I'm not sure why it's still loading. The language server crashed. Oh no. Okay. Let's see. Can we reinstate it? Language server, please. Damn, we crashed the entire LSP. Wait, can I language server? Can I restart the? No. Okay, C++. Restart IntelliSense for the active file. What? Am I missing something? No, that returns a bool. Okay, let me reload the window. Let's see. Are we back? Let's see. Perfect. Okay. So what we're going to do is whenever we insert something, we assert that it is free before inserting it. Which I think it's relevant because when I did the arbitrary insert, I think I put it before it, yeah. And then when we delete something, so bk said it's free, all of these instances need to go. So this guy no longer, this guy is no longer, this guy is no longer, right? And this guy is also no longer. Perfect. So now what we need to do is when we remove something from the red black tree, we at least need to assert that that thing is actually free, right? So bk is free. So maybe it is not in the red black tree, but it is definitely the case that it has to be free, right? So we would like it to be like, oh, right, assert that this thing is actually in the red black tree, but making that check is it like has the same complexity as the removal, so it isn't worth it. But we at least can check whether or not it's free, so as to flag some issues that may happen. Call to undeclared function do not support. Okay, is pref free? Wait, do we not have this function in the header? Oh, block is pref free. There you go. I think bk. Oh, we had it as prev free. Okay. I think it's better if we just do this. Actually, no, let's leave it as prev free. Yeah. Log prev free. Yeah, and then we just modify the call. That's actually in the wrong. Yeah, log prev free. And then this guy here is the one that needs to change. I can't change because you can blame me on my left side brain. Okay. Perfect. Okay. So if we go back to where we were here, now we can assert that both blocks are free and perform the removals beforehand, right? So this also assumes that both are free blocks and both have been removed from the red light tree, right? Perfect. So I think that if we hover our mouse over it, we're going to see the comment. Hopefully. Seems like not. Okay. What a shame. So once we have those preconditions in place, we know they're no longer in the red black tree, so we can just do any sort of modifications we want. And what we're going to do is we're going to simply set the size. We're going to set the size of block 1 to be what? So we need to know what the sort of new size is going to be. And the new size is just block 1's current size, so without including its header, plus the header of block 2, or like at least the size indicator of block 2, plus the actual size of block 2, right? Block 2. And so basically what it looks like is we want the size whenever we coalesce blocks, right? The new size is going to be the size of the current block, which is this, without including the size header, plus the header of the next block, which is this guy. Well, not the header, right? But the size indicator of the next block, plus the size of the next block. So it's going to be all of that region, right? It's going to be this entire region. Perfect. So that makes sense. That's going to be our new size. And then we simply set the size of block 1 to be exactly that, right? After that, we also need to set the prev3 of the block that was block 2's neighbor. So what we're going to do is we're going to say bk set prev3 of block 2's. Actually, okay, so I think this is one of those moments where we just say, well, there's no need to set prev3 of next block of block 2, since block 2 is already assumed to be free. So what I mean by that is that if block 2 is free already, then it means that the prev3 of its right neighbor already says free. When we coalesce, that fact doesn't change. This huge block that we just created is still a free block. And as such, we have it, right? Yeah. So this is logic, right? Pay attention to this logic when writing realloc. So for realloc, things may change a little, right? Things may be different, but for free, that it makes total sense. So I think the only thing we need to do is set the size, right? So over here, if you have these two blocks, right? Which in fact, I'm tempted to just grabbing one of these blocks and making it like a miniature version of itself. Something like this. Then I grab it, then we put it over here. Yeah, and then we shrink the user data section, which we're gonna just call extra, and then we shrink everything so that we can see the blocks better. Yay! Okay, perfect. So there you go. Oh, sorry. Okay, and I want to color the extra section with some sort of special color so as to differentiate it from the rest. I'm just gonna send it to the bottom. There you go. Okay, perfect. So if we have two blocks, right next to each other, what we're doing now is, by merely setting the size of this guy over here, we're simply just, skipping past all of this stuff. So if we set the size to something, whenever we're looking at this block pointer, we're going to skip all of this and change this size to the new size, right? New size. So that's the only modification we need to perform, because once that happens, this block is equivalent to a block that was just returned from the user, for which we don't know what the metadata contains and don't rely on it. And as such, we're able to just, expand the entire block with a single instruction. We don't have to set the pref free. The pref free for this case stays exactly the same. So I think everything is fine, right? Yeah, I think we're just good to go. I think we're gonna return a void instead. And that's it, right? We simply just return. That's all. Interesting. Yeah, that's all we need to do, I think. So let me know, guys, if you disagree. Maybe there's something I'm missing, but I think that's the only thing we need to do. So when we're coalescing with the right block, we know that our current block is already not in the red black tree. And the only thing we need to do is remove the guy that's next to us from the red black tree. So we remove from the red black tree the next block. Right. After that, we can call coalesce blocks. And which blocks are we going to coalesce? Well, the current block and then the next block. So this is already done. We remove it from the red black tree. We coalesce with the right block. We merge the blocks, which is exactly the same. But Past Bryce, thank you for following. Yo, I have another follower. Yeah, I'm a moment. Let's go. Yay. But yeah, so we coalesce with the right block over here. We merge them together. And after that, we fix the metadata. So we already thought about this. We don't really need to set pref free of the next block. We don't need to do anything other than the size. So that says goodbye. And this seems to be the only set of things we need to do, right? Because once they're together, we remove this, blah, blah, blah. And then we need to put it back in the red black tree. But remember, we wanted to do that later. So this is all we need to do, right? Where's the block? Now, notice, if the left block is free, then it means that all of the metadata it had has been restated, right? Which also means that we're able to access the footer of that memory block to know the size by which we have to jump to the left to get to the header, right? So if that previous block is free, then we can feel free to access its footer. So what we're going to do is we're going to say, well, uint32t, the previous block size, it's going to be, so currently we're positioned at the header of our block. If we go back 1, 2, 3, 4 bytes, we'll end up at the footer of the previous block. So what we're going to do is we're going to say, well, treat this as a block footer pointer. And we're going to be pointing to what? Well, we're going to be pointer at the beginning of the heap. To it, we add the offset that's represented by our block pointer, block heap pointer, and we subtract the full, or like however big the footer is from that position. So we first reach the header of a block and go back however many bytes long the footer is, and then we're going to end up at the beginning of the footer, right? This, of course, needs to be so this thing goes first. There you go. And then from it, we remove the size of the block footer. Incompatible pointer to integer type. Oh, of course. Now we need to subtract, sorry, not subtract from it, arrow into the size. If the, whoa, what's happening? Expression must have pointed to structure union type, but it has type char star. Oh, we just need to enclose all of this in parentheses and then access the size member. Hello? Oh, there you go, size. Yeah, perfect. Okay, now we know the previous size. And so what we need to do is go back by that many blocks. So we create a heap pointer to the previous block. And where does that heap pointer start? Well, we are going to start at our block, and we're going to go back however many bytes are occupied by the user section of that block. And then we skip the size metadata, which would be the 4 bytes included in the uint32. Right? I think so. Yeah, I think we're fine. So from the current block, we skip the user section of the previous block, that we end up at the first byte of the user section of that previous block. And then we skip the size metadata of that previous block. So we ended up the first byte of the size metadata, which is the first byte of the block. And so now we have a heap pointed to the block. And what we do after that is basically exactly the same, right? We remove from the red black tree this little guy, red block, right? And then we coalesce the blocks. Which blocks? Well, we're gonna coalesce prev block with the current block. And once that's done, we're gonna make block be equal to prev block. Because now the big blob, the big block starts at where prev block starts. And once that's done, we've done the coalescing. So we're fine with the coalescing. What we now need to do is we need to reinsert it into the red-black tree, right? So now that everything's done, now that they've been merged, now that we are happy, sunshine and rainbows, we simply call, well, we set, I would say, okay, for this block, we're gonna set it to be free. So my block is going to now be free, right? And then once that happens, we're going to insert into our red-black tree the block that we just talking about. Give it a second. The C extension in VS Code is really slow. Let's just give it a minute to catch up. There you go. Perfect. So now that we reinserted into the red-black tree, this is a duplicated comment. We are setting the free flags, but those are already set because we're doing it right here, right? The left-right parent caller flags are set by the red-black tree because it's something that just belongs to the red-black tree. And as such, I think we're done with free. Yo, let's go. I think, yeah, I thought it was going to be way more complicated, but I feel very happy about the fact that it seems like our decisions have been correct. The fact that, you know, the flow, at least I felt, though, you guys know that I always say, like, the beauty of your code is like a little bit of an indication of how good you're doing, right? That's not always the case. But when a code starts looking very messy, where it's hard to keep track of things, you know there's something that you're doing wrong. I think maybe some of you may disagree, maybe some agree, but I think that the development flow that we had for free was like very natural. We just were like, oh yeah, this guy needs to be free. Set its size, put them together, return, and that's it. Like it reads almost like actual text. So it feels like a nice indication that hopefully we're doing good. I'm not sure. And we did in 30 minutes, which is a record. Yeah, so I guess maybe the free function is not as complex, probably. But yeah, yo, let's go. We're happy. Given that this is the case, I think we deserve a prize, and the prize is committing this to GitHub. So git add dot git add dot git commit dash m. We have a feat. No, introduce, or well, initial implementation of free, not tested. Okay. Important and not tested because oh, new message chat. ZM! Oh my god! It's ZM! He's back. They're back. They're back. Committing without running. Oh yeah. Yeah. So I included in the message not tested. I just want to do it in case my computer explodes and then we lose all progress. So so I just wanted to do it. So the not tested part is there, and then we're gonna add the tests and run the code and etc. But yeah. You know what I should have done instead? I think I should have just created a branch and then push it there. I think that would have been way more reasonable. That's a shame. Okay, let's actually do that right now. I have been practicing Git. I've been practicing Git, guys. So trust me, this is gonna be wonderful. So we, okay, what can we do? So we check out a new branch, right? And we're gonna call it feature free. Perfect. That guy has the commit that we need, and now we're just gonna reset. Let me make sure that I'm in the correct branch. Yeah, no, git checkout main. Now we're gonna reset main to be one below the head. Yes. And so git branch. Yes, so if we do git log, we should not see that last commit. Perfect. And if we check out free, check out feet slash free, we should be able to see, ooh, git stash. We should be able to see that comment. Yes, okay. Git log. Perfect. Okay. Sounds good. And now, yeah, now we have like, let's see, message. Creating feature branches is good practice, but for small hobby projects, I think it makes sense. Oh, when you are at the point where you have a stable main, which always compiles and works, and you want to keep it that way. And at early stages, when you're actually implementing cool functionality and stuff doesn't really work, yet it makes more sense. Yeah, although my hobby projects are a mess. So maybe don't listen to me. Interesting. But yeah, so it's like it makes sense for me to push something. Like I want to push something when it's like actually working and it's like, there. Um for that reason is that I your suggestion that like, oh, you didn't test the code is actually pretty right. Because I feel like if we push it to a feature branch is better. Just to keep that separation of saying this thing is not yet ready. It's still in development. But yeah. So I don't know. I'm glad to see your bags, DM. So I'm not sure if you've been joining this the stream, but it's very fun because we have done a lot of stuff. So we translated the entire Red Black Tree class from C++ to C, which was very successful, thankfully. Oh, I mean, I guess we'll see, right? But we also finished writing Malloc yesterday, and today we tested it a little. We haven't been able to test it fully since free was not yet implemented. So we were able just to test the stuff that is like, allocate and keep allocating without freeing anything. So very basic tests. Which are also not automatic tests. These are just like inspecting the memory and seeing that the blocks are actually there. One of my goals is to implement sort of more automatic tests that we can run so that, we can check the heap state and all of that. And with free, we just started writing it like 30 minutes ago. So we wrote it in 30 minutes, with is a record, right? For at least for me. And yeah, and now we are sort of now we need to test free, right? Yeah, nonetheless, I think okay, let me make sure. Sorry, I think it committed it. Wait, git branch. Git branch. I think it committed it, but it didn't push it. So git push set upstream in origin feed slash free. Perfect. And then I need to check out main, make sure that we have everything. Oh, okay, I think that's because of the reset we made. So I'm just gonna do full with lease. Mainly because I know I'm the only author. So it definitely there's no problems. Do we have all the branches? I think we have the Malloc branch, the Malloc rewrite. Oh my god, reset. Make a branch. Git branch. Oh my god. Refactor malloc rewrite. Yeah, so git checkout refactor slash malloc rewrite. And let's make sure that everything is pushed here. So git push. And we are good to go. Perfect. Git checkout main. Okay. Git branch. Git branch. Perfect. Yay. Um So, oh, sorry, let me check out the feature-free branch because that's where we're writing the code. Yeah, perfect. So, yeah, I mean, everything's committed. Now we need to add some tests, but I have to go soon. The stream goes until 10 a.m., mainly because, I have to go to the internship and all of that. So I still have other responsibilities, unfortunately. If I could, I would stay here like the entire day. Um, but yeah, so now we'll be able to expand this test and then add a add some tests to free, test free, then test free, and then ah ah test malloc, test test free. Perfect. Okay, great. So now this is gonna be the thing we're gonna fill out tomorrow, as well as this because we did a very basic test. But yeah, everyone. Yeah, I think let's end the stream. Let's get some 7 minutes back from our usual end time. And yeah, it was very nice seeing you guys today. Hopefully we can continue with the project, and I think tomorrow we're gonna be able to test free. And once we test free, once we know free is right, we're gonna be able to actually test malloc to do like all the weird interactions between the two. And after that's done, I think we're gonna be realloc is hopefully gonna be relatively simple. You know, I don't know, but realloc is hopefully relatively simple. And yeah, let's go. I think we're nearing the end of the memory allocator, which is very exciting. But I hope to see you guys in the future. Think here we change. There you go. Whoa. All right. Yeah, I have to see you guys in the future. Tomorrow, same time as usual. Check the schedule on the Twitch. It's at we always start at 10. No, 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 no. At 7:15 a.m. Okay? Grab that hour in your mind. Every day, 7:15, and we go until 10 a.m. Yeah, perfect. I mean, now that it's nearing the end, yeah. Everyone have a good day. Oh wait, I saw more people joined. Oh no. Anyways, in, to the new ones who joined, we're just finishing the stream since I gotta go to work. Well, not work, but to the internship, and they're gonna fire me if I if I don't go. So yeah, George Orwell, thank you for following. Damn, George Orwell followed us, guys. Yeah, okay. I'm saying more goodbyes than a poor circus, right? Like it's like a saying, when a poor circus is like, oh, bye everyone, bye. We're so thankful to have you, just so that people like stay in the circus because you're saying goodbye so much. So- but I don't know. I would prefer to stay. But yeah, good luck with the internship. And yeah, thank you very much. And Morning Sci-Fi thinks it was a cool day to stop by. Yo, let's go. Tomorrow is gonna be a cooler day because tomorrow is where we're gonna actually test the everything. So, Coding Barra, hello, hello, and goodbye because the stream is just finishing. But you should join tomorrow's stream. We start at 7:15 and we go until 10 a.m. Okay? But yeah, good luck, everyone. We'll see you tomorrow. Bye bye. And keep thinking about the code. Keep thinking about the code and think, was there a mistake? Is there a bug somewhere? and then tomorrow we'll take a look at it. Okay, bye bye. Yo.